Hey, thank you very much for the invitation. I'm really sorry that I'm only participating online. I congratulate the participants who were brave enough to travel. I still feel complicated from where I'm living. My talk today, I saw this program is on commutative algebras, representation theory, and special functions, and I will today restrict to the last two. So there is some representation theory, and there is hidden some special functions. There are also algebras, actually, of course. Anyway, it's a very classical theme. And I didn't expect to be able to contribute anything in this topic, but surprisingly, there were still some things left that I could do. And it's, there it is. So it's a very classical problem. If you have a Lie algebra or a Lie group, and you take tensor products and you want to decompose the tensor product of irreducible representations in irreducibles again. Very classical problem. And so that's why I thought I couldn't do anything. And it's very well known that that you can do all these computations actually in the character ring. So if you want to calculate these multiplicities, you just multiply the characters and decompose in the irreducible characters. So this turns this problem into a problem of symmetric functions, if you like, and so this brings you kind of in the area of special functions, very elementary special functions though. So here my notation is S lambda is the character of an irreducible representation with highest weight lambda. I will be a bit informal about my notation, and introduce notations along the way in order to not make the presentation too heavy. Anyway, so it's these red coefficients that we want to compute, and well, there are of course a great deal of formulas and algorithms to do that. These are very complicated coefficients in general. Really, there's not much hope on very explicit formulas that describe all cases, but there are combinatorial algorithms to compute these coefficients, and a very important one is the Brouwer-Klimek rule. It's based on the wild character formula, and basically what you do is you take one of these characters, decompose it into monomial symmetric functions. That means that you compute the weight multiplicities of that character, and then with this, using that expansion, you multiply with the other character which you have left unchanged, and so you get an expansion here in terms of weight multiplicities and, well, some orbit sums of characters. I don't want to go into detail. This is a very general technique. The point is that here you get a very big expression with many terms that you have to combine. You don't really get a very simple formula for these expansion coefficients, these tensor multiplicities that way. But on a computer, it's very suitable for computer computations and to compute concrete tensor multiplicities with specific weights given. Well, another famous way to compute these coefficients is like the Littlewood-Richardson rule. That would be for SLN, and then there are generalizations to other type of other types of simple Lie algebras, and those formulas are again combinatorial algorithms that given lambda, mu, and nu tell you how to compute these coefficients. But again, it's like not a closed formula. You have to do many countings, and then finally you get some answer. So, well, In this talk, it's told in the title, it's about the Pieri formula. And so what that means is that I will be concentrating on in the case where one of the two weights here, let's say mu, is a fundamental weight. So it's kind of a small weight, not very big, and that makes that dramatically simplifies the situation. And in that case, there's much more that you can do explicitly, and so that's the goal of my talk. Well, if the fundamental weight is minuscule, it means that it's the weight is minimal in the dominance order. Then actually the Klimek rule or the Littlewood-Richardson rule, they become very simple, and they give rise to this type of expansion. So if mu is a minimal fundamental weight, then this product just expands in this way. So it basically translates of the general representation over some weights in the orbit of the minimal fundamental weight, and in such a way that you stay within the dominant cone. So here is the notation that was missing. W is the Weil group, and P plus is the cone of dominant weights. So this is a very well-known formula, which gives you the tensor decomposition if lambda is any dominant weight. So S lambda is the character of any irreducible representation, and mu is a minuscule fundamental weight. Okay, so this was formalized due to Cass, I think, from '87. I don't know, maybe the formula was known before, but this is what kind of the earliest places where this formula can be found. Okay, so this works very well, for instance, for SLN. If you have SLN, so this is the classical example. Well, then the fundamental weights and the dominant weights, they're usually written in terms of partitions, and the fundamental weights correspond to partitions with a single row, so 1R. And then this rule tells you that if you take the tensor product, then all partitions that appear in the decomposition differ from the original partition lambda by a vertical R strip. So that means that you add R boxes to lambda in such a way that you still maintain a partition. Well, you can do that in several ways, and if you sum over all ways, then you get this decomposition, and all the multiplicities are equal to 1, so it's multiplicity free. That's in general with which you see from the Cass formula. Well, this is the classical formula actually due to Pieri. Well, maybe this is a dual formula, but usually the Pieri formula is formulated not for for partitions with one column, but with one row. But anyway, it's basically this formula. This means for SLN, this gives you all the expansions for tensoring with the fundamental representation. But unfortunately, if you go to other types, then the fundamental weights are usually not minimal, not minuscule. So it means you cannot use this formula to compute tensor products with any fundamental representation in the other types. And so that was the goal. That was my goal, to try to extend these cases and cover well, at least all the classical algebras. Mind you, there are formulas available for the classical algebras, so the ABCD series for tensoring with the fundamental representation. But usually these formulas, they are like combinatorial in nature again. So they give the tensor multiplicities in terms of some counting problem. You have to count semi-standard tableau, things like that. So it doesn't give you really a short, compact formula or answer for the tensor multiplicities in those cases. Not like in type A here, right, where we just see we have a very simple formula telling you which weights appear in the expansion, and the multiplicity in this case is just 1. Well, the formula that I'm going to present here will not be combinatorial so much. So it will be more like a formula of this type. In order to present the formula, I have to introduce some notation. So again, the formula that I present doesn't work really for all fundamental weights of any type. It works for fundamental weights which are called of classical type. So what does it mean? It means that if you take the weight and pair with the co-roots, positive co-roots, then this number should not exceed 2. If this bound is lower to 1, then you get exactly the minuscule fundamental weights. But if it's 2, then you get a little bit wider range of fundamental weights, which are called in the literature fundamental weights of classical type. So this is the type of weights that the formula can handle. So tensoring with a representation with the highest weight of classical type, that is the situation that the formula can manage. And so in the case of classical algebras, all the fundamental weights are actually of classical type. So that's good news. That means that the formula can compute the multiplicities for tensoring with the fundamental representation in all the classical cases. In the exceptional cases, you will always miss a few fundamental weights which are not of classical type. For instance, for E6 you miss 1, and for E8 you miss 6. So it's not a complete formula still, but for the classical algebras it's a complete formula. So okay, some further notation. P plus is the dominant weight system. I mean the dominant weights in the highest weight system, in the weight system with highest weight lambda. So these are all the dominant weights smaller and equal in the dominance order than lambda. This W nu refers to the stabilizer of nu, so the Weil group elements with stabilized nu. So I will use this notation. And now I think I have all notations in place, and I can show you the formula. Lambda is any dominant weight. Mu is a fundamental weight of classical type, so which pairing with the co-roots doesn't exceed the bound 2. And then the tensoring gives you the following multiplicities. Well, I will slowly explain a few things in this formula. First of all, here is a sum over the weight system. So this is the Weil symmetrization of the dominant weights smaller than mu. You have to sum over the whole weight system such that lambda plus nu stays dominant. So that's a good thing. Usually if you use the Brouwer-Klimek rule, you sum over a larger set, and then you have to reflect back to the dominant cones using shifted reflection relations. And that means that you have to do a lot of computations before you actually get the multiplicity as a result. Here, that's not the case. Here the summation is kind of truncated to the dominant cone automatically. So you see immediately which multiplicity, which characters appear with non-zero multiplicity, and here you get a closed form for the multiplicity. I will explain a little bit more about this this coefficient. So this is the generalization of that formula of Cas for the minuscule fundamental representations if you lifting it to the fundamental representations of classical type. One thing that's important to notice is that now the multiplicities can be higher than 1, so it's no longer multiplicity free. Okay, so what are these numbers here? Here, nu plus is just the dominant weight in the orbit, in the Weil orbit of nu. So, and here, so you have to sum over certain weights. And what do we have to sum? Well, a product of factors. This is a basic factor. And it basically counts a small part of the Weil orbit. It's a very small part of the Weil orbit of mu. First, you have to map mu to the same chamber as nu, and then you stabilize. Then you act with the stabilizer of nu, and then you count all the elements for which rho plus lambda plus nu is in the dominant cone. This is it's not such a big number. And there are these R mu kappas. Well, what's that? If you put here lambda equal to 0 and restrict here to dominant weights, and this nu is not necessarily a dominant weight, but if you restrict to dominant weights here, you get a kind of uni-triangular matrix. And if you invert this uni-triangular matrix, then you get these coefficients. These here, mu and kappa, are always dominant. You can do this explicitly because this is uni-triangular. And so if you do it explicitly using Gauss elimination, you get this kind of expression. This is the basic ingredient, and this is just obtained from inverting this number for lambda equal to 0. So those are the coefficients here. Here they're written as a very big sum, because in general it's hard to give a compact expression for this. But if you're in a concrete root system, so from type B or type C or whatever, then you can usually do this inversion much more efficiently and get a very compact formula for this coefficient. I will show you later on some examples. Anyway, so of course, if the fundamental weight is minuscule, then this whole formula kind of collapses to the formula of Katz. Then this weight system is just the Weil orbit through mu, and all those coefficients here are 1 in that case, and this sum becomes actually a sum of one term, because then nu plus and mu are the same. So because this will be just the same, and nu will be in the same orbit as mu. So, and then the formula collapses to the previous case. But if the fundamental weight is not minuscule, then this formula becomes quite a bit bigger. But still, it's quite kind of satisfactory that that you can write such a formula down completely explicitly and irrespective of the type of Lie algebra. So this works for all types. Yeah, this name fundamental weight of classical type doesn't mean that it only works for classical Lie algebras. Exceptional Lie algebras also have fundamental weights of classical type. For instance, the minuscule weights and the quasi-minuscule weights, and for all these cases, this formula works. Everything is kind of concentrated. The building block for this formula is kind of this number here, counting this small part of the Weil orbit through mu. So I want to say a little bit more about the structure of these numbers here. If lambda is strictly dominant, then yeah, I should return. I'm sorry. If lambda is strictly dominant, then you always remain in the dominant cone, and so then this number here, yeah. Oh, I forgot to mention, this is just the size of the orbit, right? So if lambda is strictly dominant, then this is just the size of this this orbit, and it's only when lambda is not dominant but not strictly dominant that you actually have to leave out a few of the that's what's happening here is that if you compute the whole orbit, then you get what I call the bulk value, and the ones that you have to leave out are these where you end up outside the dominant cone, and this is what I call a boundary defect correction. Now it's very easy to compute this. That's just the order of the orbit with respect to the action of a stabilizer. So you have closed formulas for that in terms of the root data. And it's also not difficult to compute this boundary defect correction. So when you get out of the dominant cone in terms of the root data, here are some explicit conditions. You basically have to check that there are simple roots perpendicular to lambda and u, which have an inner product -2 with eta. So this gives a kind of criteria for this condition in terms of the root data, which is very easy to check. Okay, so that's the general formula. It's a bit difficult to appreciate at first, but I will show some examples in small cases now. The first case beyond the minuscule fundamental weight is the quasi-minuscule weight. So, and that means that mu is the highest short root of the root system. The corresponding representation is usually called the little adjoint representation. If the algebra is simply laced, then it's just adjoint representation. But if it's not simply laced, it's a representation corresponding to the highest short root. Well, so if this weight is quasi-minuscule, then the above formula simplifies in the following way. The weight system in this case is just equal to the orbit, the y orbit, through the highest short root. So it's given by all the short roots, and the zero weight. So there are only two orbits, and you get in the tensor decomposition the kind of minuscule expression corresponding to the orbit, and here another contribution corresponding to the zero weight. So that gives you a copy of S lambda, and it's only this multiplicity which can become bigger than 1. Here it's just multiplicity free in this orbit. Well, here are these numbers. You see, it's not really a combinatorial formula because we are subtracting things. It's not a positive formula. But of course, finally, the multiplicity will be positive. And if you really compute, so here is the bulk value of this number minus the boundary defect correction, and for this one you have something similar but with lambda equal to 0, and if you subtract, then you get that this multiplicity is just equal to the number of short simple roots that are not perpendicular to lambda. And well, this case reproduces a familiar formula, because the case of quasi-minuscule fundamental weights was also worked out by Cas, and the final result, of course, agrees. Right, so that's a nice test case of the formula in the case of quasi-minuscule fundamental wage, we just get the formula of CAS. Well, that's basically what I want to show in general. And now in the rest of the talk, I just want to show some explicit examples for classical root systems. I forgot that before doing that, I wanted to give a small idea of the proof. The proof is based on a recurrence relation and it's of this type. If it's basically an explicit expansion for the character multiplied by another polynomial in the character ring, and this other polynomial usually people use for this other polynomial the monomial symmetric, the symmetric monomial, and then this expansion can be computed, but it usually takes you outside of the dominant cone, and you have to reflect back, and that's why these expansion coefficients are kind of hard to compute if you use the monomial basis. So here we use a different basis which expands in monomials in this way. Here are the monomials. The coefficients are these orders of stabilizers. It turns out that with this basis, you can compute this expansion completely explicitly in terms of the inside the dominant cone. So here is where these coefficients n appear. They appear in the expansion of these products. And well, how did we get this formula? Well, a few years ago with Erdal-Emsis, we derived a difference equation for the Heckman-Opdam hypergeometric function. And as a degeneration of that difference equation, if you degenerate the hypergeometric function of Heckman-Opdam to a well character, then you get this recurrence relation. But so I insist that the nice thing is of this formula, the nice feature compared to what you usually see when using monomial symmetric functions, is that here everything stays within the dominant cone, and you have a closed form, closed expression for the expansion coefficients. Well, with this recurrence relation, it's not so difficult to find the Pieri formula, because first you specialize the recurrence relation to the case lambda equal to 0. So here is that formula. So here I multiply with s lambda, but with lambda equal to 0. So I multiply it actually with 1. And so then the formula here just gives a decomposition, the character decomposition of this polynomial in the character ring. Yes, so sorry, I will return. It's just this formula for lambda equal to 1, lambda equal to 0. And this is 1, and I get a decomposition of this basis element in the character basis. Here it is. And now if I invert this relation, decomposition or an expansion of the character in terms of this basis, and if I know how to multiply characters with these elements, which I know from the recurrence relation, then I can use this expansion to compute the multiplication of a character by the fundamental representation of classical type. And so that's how you get the Pieri formula. The character formula plus the recurrence relation gives you the Pieri rule. Well, so that's the idea of the proof. It's not simple, not difficult, but yeah. The challenge is of course the technical details. Okay, so now I'm ready to show a few classical Lie algebras. So here is type B. So it's the orthogonal algebra in odd dimension. Here are the simple roots. Here are the fundamental weights. This weight here is the spin weight. It's a minuscule, so I will ignore it because that is just governed by Cass's formula. I will concentrate on these fundamental weights. The first one is the quasi-minuscule, so it's also covered by a formula of Cas. But beyond that, it becomes it's no longer quasi-minuscule. For instance, for r equal to 2, this is the adjoint representation, and then it becomes more complicated. Well, the Weil group here is just a group of signed permutations acting on the unit basis. So, well, with this information, we can make the formulas very concrete. So here is the concrete result. Here's the recurrence relation. The fundamental weights correspond to these one column partitions. And so if I multiply, I get the recurrence relation. I'm summing over index sets, and I'm summing over signs because I have this group of signed permutations. And basically, I add or I subtract units to the weight. And the weights are, in this case, encoded by partitions again. Now, what's this polynomial which I multiply by in the recurrence relation? It's this one. It's basically an elementary symmetric function, but there is this shift. Yeah, you see kind of quadratic transformation maybe here. So, but that's important. It's not the usual monomial. It's with this shift. Then with this shift, this expansion becomes very simple. That's the idea. So here are the recurrence coefficients in this case. Here is the bulk value. It's just binomial coefficients. And here is the boundary defect correction, which detects if you leave the dominant cone. So here is written completely in terms of the concrete root system. This I don't want to go into it's not very difficult, but this is a explicit translation of this general formula in terms of arbitrary root system. So in type B, it becomes this. So basically, you have to check whether if two parts in your partition are the same, and then if you would add something in the orbit of the fundamental weight, then it detects when you get out of the dominant cone or not. And well, there are very limited possibilities actually to leave the dominant cone, and so that gives a small combinatorics that's easy to compute. Again, if lambda is strictly dominant, then you just can forget about this. This is always 0, and then this is just the expansion coefficient equal to the bulk value. This is the one column character formula in type B. So we had to expand the fundamental representations, the characters, in terms of these polynomials. And in general, I could only do this with this Gauss inversion, so it was a very big sum. But here in the concrete root system, you can do this inversion much more compactly. And actually, these are the inversion, the coefficients of the inversion. So this is the character expanded in these shifted elementary symmetric functions. This is just a shifted factorial. So it's a very compact formula in that case. And if you combine this one with the recurrence relation, then you get the Pieri formula in the type B case. So here is all this sum over subsets. Basically, you're symmetrizing here over the Weil group. And here is the coefficients. These are coefficients. Now they're called B because we're in type B. And these are these small, these shift quotients of shifted factorials. So it's very explicit. And this is the coefficients from here, which is the bulk value minus this correction. So it becomes a very explicit formula in that case. And well, that's very satisfactory. You can do this also for the other classical types. And surprisingly, if you do this, for instance, for type C, things become a bit more complicated. But before I go to type C, here I've listed some really small cases. So for r equal to 1, this is the quasi-minuscule case. So this is the little adjoint representation. Then this formula becomes very small. And and it becomes very explicit here. These numbers become very explicit. This delta is just a kind of Kronecker delta. Well, what I mean is if the argument is 0, it's 1, and otherwise it's 0. So it's very compact here. And for r equal to, that's the joint representation, then the formula becomes a bit bigger. You have again an orbit with which is multiplicity free, and then an orbit which looks a bit like quasi-minuscule, and here something below. So, and again, these coefficients, it becomes really concrete if you work this out in these cases. So you don't have to do counting or stuff like that. It really gives you the formula immediately. Now, to end, I want to show type C. Type C, here is the root system, and here are the fundamental weights. Fundamental weights are again one column. The one group is again the group of signed permutations. Now, there's one difference here compared to type B. It looks very similar, but the difference is that now dominant weights are comparable in the dominance order only if they differ by 2. So E1 and omega 1 and omega 2 are not comparable, but omega 1 and omega 3 are. So it depends on that, and that makes the formulas a little bit more complicated, as I will show you now. I just only show you the Pieri formula, the final result, so I don't show the recurrence relation and whatever. Here is the Pieri formula. It looks very similar, but it turns out that these inversion coefficients are a bit more complicated and in fact a bit more interesting. So this part of the formula is very similar. You just have to make small adjustments for the root system. But now the underlying recurrence relation is stemming from these polynomials. So it's again a symmetric polynomial shifted and another symmetric polynomial backward shifted. You have to symmetrize. And that's the appropriate basis in this case. And well, that has as a consequence that these coefficients finally, they become a bit more complicated, but you can still compute them explicitly. So in type B, we kind of had something like this only, but in type C, you have to subtract some corrections. And in these corrections, it's very interesting, the combinatorics that are of these corrections, tangent numbers or Euler-Zeg numbers, as they're also called, appear. So these are just the coefficients of the Taylor coefficients of the tangent function, or if you like, the tangent function is an exponential generating function for these tangent numbers. So these numbers appear now in the inversion formula for the coefficients. So anyway, this just to show that you might think, oh, type B, type C, it's all of the same, but no, type C becomes a bit more complicated, and in type D again, it's very similar to type C, and you also have these tangent numbers appearing in the tensor multiplicities. Okay, well, this is just to have an idea of this formula. It's impossible in a talk, I think, to digest properly all these formulas. The talk is based on this paper, a Pieri formula for the characters of complex simple Lie algebras, that recently appeared in transformation groups. And what we used here to get the recurrence for the characters, which made possible computing these tensor multiplicities is in this paper. Here in this paper with Erdal Emsis, we derived the difference equation for the Heckman-Opdam hypergeometric function, and it's by degenerating this difference equation that we get this recurrence relation, which permits computing the corresponding tensor multiplicities. Some more papers, previous literature. So I already mentioned this paper of Kaas, which computes the tensor multiplicities in the case of minuscule and quasi-minuscule representations. Also, in the case of the adjoint representation, that case is also covered by Kaas. And well, but the formulas, well, for minuscule it really gives immediately the same thing. For quasi-minuscule, too. So the advantage of the present formulas is that you can go beyond this, and then especially for the classical root systems, this works out very well. But I should say that there are important other papers. Here is a short list where combinatorial formulas are given for the tensor for the Pieri rules. So the tensor multiplicities of tensoring with the fundamental representation in the case of the classical Lie algebras. But the difference with the formulas here is that the formulas in those papers are combinatorial in the sense that they that in order to compute the multiplicity, you have to count semi-standard tableau or variations of semi-standard tableau. So it doesn't give you really a short answer. It gives you an algorithm to compute the multiplicities. So that's the difference between the formulas here. And an advantage of these combinatorial formulas is that they're manifestly positive. I mean, you just are summing positive counting stuff. So it's by definition gives a positive number. Whereas here, there is some cancellation because you're adding and subtracting things, so that's a disadvantage of the formulas here. But they're very compact in some sense. Well, that's all I wanted to say. I don't know how I am with time, but I think I'm still okay. Yeah, thank you.
Thank you, Jan Felipe. Merci beaucoup. Is there any questions? If you're from online, please you raise your hand so I'll know that you have a question. John, please open your microphone and ask your question. We can't hear you, John. Your microphone is on.
Can you hear me now?
Yeah, I do hear you now.
Okay.
Yes, hi John.
So I have, you know the Murnaghan-Nakayama rule?
Yeah, well, there are many, but I forgot what it tells you exactly.
Oh, it tells you, well, in the simplest sense, if you take a Schur function, instead of multiplying it by an elementary or complete symmetric function, you multiply it by a power sum.
Yeah, okay, yeah.
And it does a enumerative thing about dimensions and so on. So it's actually simpler than the Pieri rule because there are fewer diagrams, but it's very easy to describe. So I was just wondering if if you happen to know, it does play a role in some geometric applications. If you happen to know if there exists an analog of the Murnaghan-Nakayama rule for other simple Lie algebras.
So I don't know really, but for the classical algebras, you would expect there is something, right? But I didn't really. But I think there should be something, but of course much more complicated than than for type A. Today's story for type A didn't bring anything new. I should emphasize, because it's much more simpler. But so I don't know. I would have to I would have to check.
Well, I would think that there must be, because you can use the Frobenius-Schur formula to relate the two, to relate the Schur with the power sum. So if you express the power sum as an elementary sum over the Schurs, I don't know if it only involves the elementary Schurs, but it gives you an explicit formula in terms of characters. So one should be transformable into the other.
Yeah, I think so too. I mean, but yeah. So I really don't know. I mean, I'm not such a big expert in type A because I mean, in type A there are so many things known that I don't know, and most of these things they don't generalize to general type at least. And but many things do generalize to other classical algebras. So I think you're right, but I can't tell you where you can find these formulas. Maybe in work of Warner something can be found, but I'm not sure. And my angle from here in this talk is I'm coming from the general complex simple Lie algebra, and then it's very restrictive. I mean, because you can't just even a power sum is not clear what it means in general.
Yeah, I was just thinking that the analog, there must be an analog of the power sum given by the Frobenius character formula. Right? The power sums are linear combinations of the Schur functions with the characters as the coefficients. So if you specialize that to the simple power sums, it will give you a way to relate them to the Schur basis. I don't know, but with I think the coefficients would be the characters for evaluated on cycles.
You are talking about classical groups, right? Or
I'm really only talking about AN. I only know it for AN.
No, but
it's very useful.
Yes. May I interject? The discussion is rather technical, and since we got a little delay, you might want to stay online and keep on the discussion. I would like to invite people to go to the coffee break. However, there's an announcement. Rodrigo Pimenta had to leave in a rush yesterday evening because of a health problem in his family. He won't be able to give his talk, which was the next one. So we're breaking now for the coffee break until 2 o'clock, where Alexei and Nico are giving their talks. Okay, so we'll thank Jan-Philippe again and leave John and Jan-Philippe discuss the technical issue. But let's thank Jan-Philippe once again.